know 4 words.
All right, let's take a look here. Review a little bit from last week.
No, I just know it. I don't know how I know it.
Okay, we were talking about continuity, and I'll just kind of, I bet you we can maybe even get down to the lab and start on this assignment today. I want to just quickly review the stuff we talked about with continuity, extend it slightly, just kind of finish up that section, and then you can go work on some problems. What did we say about continuity? We said when we talked about continuity at a point, so if we want to, well, I guess before I even say that, we defined continuity on an interval in kind of a functional way. How did we use a pin and say we can define continuity on an interval? A function is continuous on an interval if I can what? Draw it without picking my pen off the board, right? Okay? And so then we wanted to translate that into some mathematical statements, right? We said, okay, so continuity at a point. A function f is continuous at the point C if what? What's going on? Okay, so first of all, so the function exists. Good. So if, whoops, if,
Where can I look at those? Okay, I know it.
f of c exists, so the function is defined as c, right? That has to be true. Okay, what else had to happen?
Oh, the limit must exist.
Okay, the limits had to exist, right? And that was important because what we were getting at there was, remember with the ants approaching C from either side had to agree on where they anticipated stepping, right? So the limit of f of x as x approaches C has to exist. And then the last one was what?
The limit has to equal the f of
Yeah,
c.
good, okay. So then the value of the function has to equal the value of the limit. And really, that's the one I would claim, that sort of sums up the other two. If you remember the third one, it presumes the existence of the first two. And so really, I think that one really says it all. Okay, so.
Take your pen.
Okay, so then continuity on an open interval. It's really easy for us to extend this idea of continuity at a point to an open interval. But I guess before we go any further with this, we have to just make sure we're all clear with what we mean when we say open interval versus closed interval. Okay, so let me add a page here, and you remind me real quick. What does that mean? So if I have endpoints A and B, what's an open interval going to look like? If I were to, say, graph it on the real line, and this is A, and that's B, what would its graph look like? Think about that for a second. We're going to compare that to a closed.
Is it the
Idea?
would you like to fill in the dot and then the
Okay, very good. Very good. So on an open interval, we're not including the endpoints. Closed interval, we are.
So it's going to be in parentheses if it's open.
Right. So if it's open, we'd write it like this. Okay. If it's closed, we'd write it like that. Takes a little more ink to draw the square brackets because we have to fill in the little top. Okay, why do you suppose we call one of them open and one of them closed? It's not immediately obvious why that makes sense. Those words do, but they do. Open and closed do. Is there a leftmost endpoint on a closed interval?
Yes.
Yeah. Case closed. There is a leftmost point, and there is a rightmost point, isn't there? Right? Case closed. Is there, notice I use the word closed there, see what I'm doing? That's kind of Is there a leftmost point or a rightmost point on an open interval? No. There's not. There's not, because if I think it's like going to the door, right? If I'm cutting my distance to the door in half with every step, it's pretty clear that the limit of my motion is the door, but I can take steps forever, right? And so there is no last point. If I think I've gotten to the last point, there are actually an infinite number of points still between me and A or B, depending which way I'm walking, right? So I think that's capturing, why those words open and closed make sense there. Okay, so given that definition then, it's pretty easy for us to define continuity on an open interval. We would say that some function f is continuous on the open interval, x is greater than a and less than b, if it is continuous at each point in the interval. If that definition of point continuity that we came up with, right, that the value of the limit equals the value of the function at each point, if that's true at all infinite points on this interval, then we got it. Okay? So really, as is often the case in math, it's easier and more interesting to look for the handful of places where maybe that's not true than all the infinite places where it is. The where it is pretty boring. It's where it's not that sometimes it's interesting, right? So let's take a quick look here at some examples. Now I've got some open intervals here from A to B, right? In each case, clearly the function is not continuous, right? First of all, just identify for me, which of the three rules am I violating there? Remember, we said the function has to be defined, the limit has to be defined, and the function has to equal the limit. Here, there's no limit?
F of C doesn't.
Okay, good. The function is not defined at C. If the ant actually steps on C, he just, who knows, goes to the Bermuda Triangle or something. Who knows where he ends up. But he blinks out of existence momentarily, right? Okay, so function undefined. Oops. Okay, what about this guy?
There's
No limit. Good. And then the last case?
F of C
The
doesn't.
limit doesn't equal.
Okay, good.
I have not drawn it.
Okay, now I want to apply some words and terms to these. There are two broad categories of discontinuities that we like to refer to. One of them, and let me go back, I haven't written on the previous page. So we want to make sure we get these straight. And I think in Math Excel, they even go a little bit further than this. It's sort of unnecessary in a way, but they do, so we better deal with it. Removable versus non-removable discontinuities. Simple way to remember that. A removable discontinuity is one that you can repair by either adding or moving a single point, which seems fairly doable, right? We can just either fill in the hole, or we can move a point that's not overlapping with the hole. So if we were to go look at our examples on the next page, which two of those examples would we consider to be removable? Okay, first, good, because I could just fill in that hole, right? So he's removable. And which other one? Third one, because all I'd have to do is just migrate that point up there, right? And that one would be removable. So by just redefining the function a little bit, we could accomplish that. But how about this one? How many points would I have to move to repair that one?
Bunch.
Well,
More than
2, but I'd have to do actually quite a bit more than 2. How many? Infinite, yeah. Because I would have to fundamentally change the shape of the whole curve, wouldn't I? Right? If I were to, for example, drag this point down there, like there's a flexible piece of rope, let's say, and join that rope to that rope, well, there are an infinite number of points that are going to get affected. So that's one where it's a pretty big deal, right? I mean, that function really can't be repaired. It would have to have a whole different function that's just different in every way, right? So this one is non-removable. Okay, now I think there's the additional distinction in math itself. They say that this is what we would call right here. This is an example of a jump discontinuity, meaning that it's not infinite. An ant could, theoretically, if he's really athletic, he could jump that gap, right? But that's different from one like that, which is clearly also non-removable, right? But this is one that we call an infinite discontinuity, because you can't jump that one, right? And that's, I don't think that's really a super important distinction, but it is going to come up on your assignment, okay, the math itself. So just know that those two they mean just different categories of the same thing, non-removable discontinuities. Okay. Oh yeah, and I want to add one more thing. It's just some terminology. When we talk about the whole real line, is that an open interval or just inherently or a closed interval? If I'm talking about the entire x-axis, the entire real line, it's got to be open, doesn't it? Because there are no endpoints there, right? They just extend out to infinity in both directions. So then we would say that if a function is continuous on the open interval extending all the way from the limit as x approaches negative infinity to the limit as x approaches positive infinity. That just means all possible values of x. And so we call that everywhere continuous, okay, in math. And that's kind of our default setting, unless there are some places where the domain of the function is not defined. And we'll do a lot of work with that in the future. Okay, so. All right, so moving on. Continuity on a closed interval. Okay, this one is just a little bit trickier. It's not bad. But I want you to think about this for a second. Now, if we draw a picture. So here's our real line. That's A, and that's B. How are we going to accomplish a definition for continuity on a closed interval where we're going to include those endpoints? Any ideas how maybe we could do that? It's pretty similar to continuity on an open interval, right? How many points is it different? 2, right? The endpoints. Okay, and that's a pretty good hint. Think about that for a second. In fact, take 30 seconds or a minute at your table and just mull that one over. See if you can come up with something good. Continuity on a closed interval. Okay, so any ideas? Ideas, what do we got? How are we going to define continuity on a closed interval? Anybody got, and I don't even need a complete answer, any just ideas for a strategy? How can we define continuity on that whole interval? Right? Well, we know it's going to be brackets, yeah.
Okay, here we go.
That's right, they're still there, you know it. Is there a place we could start? We've already talked about some stuff today that might be useful, maybe. Okay, well, the function exists, true. If we wanted to, I mean, assuming that has to be true, doesn't it? It has to exist for every point where?
In between A and B.
Okay, in between A and B, sure, okay. Okay, greater than A or less than B, okay. What else has to be true? So it has to exist everywhere. We have to have, but we know that every point in between we've already accounted for, right, with the open interval. So really, we can just go back and, we've already done all the heavy lifting on some of this stuff. We could just say, for it to be continuous on the closed interval, well, it needs to be continuous on the open interval, and we already know what that means, right? But then what about the endpoints? Got to deal with the endpoints, right? Now, how are we going to do that? How are we going to do that? We can't really say a normal limit at the endpoints, can we? Right? We've already done this. We want to just fill in these blanks here, right? If I want to define continuity at that point, our normal definition of continuity at a point requires that the function be defined there, no problem, but that the value of the function equals the value of the limit. But we can't really define a regular limit there. What maybe do we have to do instead?
With the limit from the right side.
Ah, okay, good. We gotta do a one-sided limit from the right. How about that? So one thing we'd have to say is that f of a equals, how do I say that? How do I say the one-sided limit from the right at x equals a? Limit of f of x as x approaches a plus. Yeah, good. A from the positive direction, right? Okay, and same thing for f of b, right? F of b equals the limit of f of x as x approaches b from the negative, good, to the left. Okay. So sometimes in math we call this a right-handed limit and a left-handed limit. Okay, good. Let's practice a couple problems. I want you to
Why didn't you start from the beginning?
I'd go back to the very
How about that one? Find the x values, if there are any, where the function is discontinuous, right? Because where it's not discontinuous, it's continuous. So are there any places now, how are we going to organize our thinking here? What are the kinds of places where a function maybe could end up being discontinuous?
Undefined.
Okay, where it's undefined. What are the two rules that we always have to follow with real numbers? If a function would ever ask us to do one of these two things to real numbers, now you guys have already said this once this year at least. We can't divide by zero, and you can't, what else?
Square root of a number.
You can't take an even root of a negative number. Okay, there are no even roots going on there, but there is an x on the bottom, and so we got to be careful about that first rule, right? So how are we going to do that? How are we going to solve that? Let's see. There's a danger zone, right? There's a red flag that goes up on the bottom of our function. Let's just encapsulate everything in the red bubble. So that's the part of the function that could be problematic, right? That's the one that can't equal 0. So we'll just set x squared plus 1 not equal to 0 and see if there are any x values that are defined there. Are there? If I solve for x, what do I get?
Square root of -1.
Yeah. I get x squared equals -1. And so there are no real numbers for which that's true, right? And so we're okay. Does that make sense? There aren't any x values that could ever make the bottom 0, and so this one is everywhere continuous, right? No places. Make sense? Okay, but what if we change that ever so slightly? And we do something like this instead?
Wait,
Okay, that's gonna change things, isn't it? Right? There's the bubble, right? That's the part that we gotta be careful of. So when x squared minus 1 is equal to 0, those are the values of x that we can't include. Those are places where the function won't be defined. So we can solve this one, isolate x. X squared is not equal to 1. So what's x squared not equal, or x not equal to then?
positive.
Negative 1.
Yeah, plus or minus 1. Those are the values of x where it's going to be discontinuous in this case, right? Now, another question. So we know, so x can't equal plus or minus 1. Are those removable or non-removable discontinuities? And how do you know? I just briefly mentioned this, but I wouldn't be at all surprised if this one we haven't really talked much about. What if I tried to evaluate that limit? The function's not defined there, right? But let's check the limits, right? So we can see what the behavior of the function is. Where do the ants anticipate stepping? If I were to take the limits of my function as x approaches plus or minus 1, what would I get? Remember, there are three kinds of answers. So let's rehearse those real quick. Three kinds of answers that we could get if we try to evaluate limits directly. The good news, probably the favored one is get an answer and we're done, right? What was the second one?
Undefined.
Undefined. If we got a 0 on the bottom but not on the top, that was the one that was undefined, right? No limit. And what did we say that always amounted to? If we got a 0 on the bottom but not on the top for our limit. Vertical asymptote. Yeah, it always meant that there was a vertical asymptote there. And so it was a big infinite discontinuity and the function's undefined there. And then the third kind was, Campbell, I think you said it. What was it, the third kind?
Indeterminate.
Indeterminate. Yeah, if we get 0 over 0, and that just means what? More work. And they're actually, we won't get into this now, but just later on we'll come back to this. There are other indeterminate forms too for limits. We could get something like infinity over infinity, or we could get 0 times infinity. There are all kinds of things that are indeterminate. But for now, we're satisfied with just 0 over 0. Okay. So then, if this one, topologically, what kind of feature is that on our two-dimensional landscape? If I get a 1 on the top and a 0 on the bottom, vertical asymptote. Yeah. So is that removable or non-removable? That's non-removable. And is it a jump or an infinite discontinuity?
Infinite.
Infinite. Good. Good. Okay. So let's try another one. Okay, how about? Okay, how about that one? Okay, any discontinuities there? Are there any values of x for which this has to be undefined?
3.
3 has to be 3, right? Pretty easy because I can see, here's my red bubble. I can't have 0 on the bottom, right? So we know that x cannot equal 3. Okay, but what's going on there? What's going on there? If I try to evaluate this directly, what do I get? 0 over 0. Okay, so because the limit of f of x as x approaches 3 is 0 over 0, is this going to be a vertical asymptote?
No.
No, it's not going to be. Okay, what is this one going to be? Well, let's look at it and see. If I wanted to sketch a quick graph of this, and that's how we'll approach this one, how about? What is, for for values of x greater than 3, what is that going to become? So for x equals 4, or x equals 5, or x equals 3.1, or 1 billion, it's going to be 1, isn't it? Right? Does that make sense? Okay, because for all values of x greater than 3, the absolute value of x minus 3 is just going to be x minus 3, right? It's going to be positive. What's it going to be for values of x less than 3? Negative 1. You're right. Agreed. Because for values less than negative 3, that absolute value is going to have to multiply the top by negative 1 to make it positive, right? Now there's a way to show that. This is really important. This is not something that really shows up in the textbooks, but I think this is a big deal in math. Let's take this function, and I want to show you how you can define this thing in terms of an absolute value function. If f of x equals the absolute value of x minus 3 over x minus 3, let's just take this absolute value function on the top. And a really good idea when you're dealing with trying to do some analysis on a function that either an absolute value function or a composition of an absolute value function and other stuff, is to rewrite the absolute value function immediately as a piecewise function. Okay, and this is, I know this looks like there's a lot of ink involved, but it's not a big deal. What is the absolute value as a piecewise function? Absolute value of x minus 3. What are the cases? I mean, what are the things that the x minus 3 could do? If x minus 3 is positive, you already told me, the absolute value function does nothing, right? So when x minus 3 is greater than 0, the absolute value of x minus 3 is just x minus 3, right? Okay. When x minus 3 is less than 0, it's equal to, it's the opposite of that, right? It's going to multiply by negative 1. So I'm going to get negative x plus 3. And then the in-between case, when x minus 3 equals 0, it's just equal to 0, right? Does that make sense what I've done there? Okay, and that's always how an absolute value function can be broken down into a piecewise function. Okay. Now, one thing we want to do is we actually want to rewrite those domains. We don't really want to leave them like that. We'd rather solve for x in each case, which means we're just going to add 3 to both sides. Right? So let's do that real quick. So if I add 3 to both sides, I just get x is greater than 3, x is less than 3, or x equals 3, right? Okay? So how do I add that stuff up here? Well, it's no big deal. If I'm going to divide the absolute value of x minus 3 by x minus 3, then can't I just define this as this piecewise function, but in each case I'm just going to divide by x minus 3, right? So on the top, I'm going to get, for values of x greater than 3, I'm just going to get x minus 3 over x minus 3, which is what? 1. That's 1. Okay, for values of x, for values of x less than 3, I'm just going to get, I could just make that a minus the quantity, x minus 3 might be easier, right? Over x minus 3. And that's going to go to what? Negative 1. Yeah. And then in between, what am I getting in between? Well, when x equals 3, it doesn't matter anyway because the function's not defined there, right? And so x can't equal 3 anyway, right? That's off limits because we can't have a 0 in the bottom. Agreed? So then if I were to graph this guy, there's 3. Doesn't it just look like this? Oops, 3 in a bad spot. That's my function, right?
Yeah.
Okay, so what kind of discontinuity is that? Jump, yeah. So removable or non-removable? Non-removable jump discontinuity. Very good. Okay, I'm going to show you a picture theorem, and then, well, there's no sense us going down to the left here. I'll get you some time on the left and we'll work on this stuff. How about this? Let's look at the intermediate value theorem. Okay. This is what we call an existence theorem. Right. It's an existence theorem because, and they always go the same way. Existence theorems in calculus just say, if you meet these criteria, then we can guarantee the existence of something special. Okay, so that's the way this one is too. If you meet the criteria, then something is going to exist. Some important condition is going to exist. Here's how it goes. If f is continuous on the closed interval from A to B, and k is some real number, okay, which is between f of A and f of B. So I'll just say k is an element of the reals. That just means element of. You familiar with that? Okay, element of, and then that capital kind of script R just means a set of real numbers. So it's just a real number such that k is either greater than f of A and less than f of B, or k is greater than f of B and less than f of A. In other words, it's between the two values, right? Then there exists, there's that word exists, right? At least one number C in the open interval A to B such that f of C equals k. That's a mouthful. That's probably thinking, wow, what's all that gobbledygook? So easy to think of and see in terms of a picture. All we've said there, if we draw a picture to match this, is this guy. If we just pick two, let's just say A arbitrarily is there, and B is here. If I've got some continuous function, one that I can draw without picking my pen off the board, that's defined between this point and this point, right? Now this is at A, and isn't the value of y there just f of A, right? So the coordinates in order to pair are just A, f of A. These coordinates are just B, f of B. And, you know, it could have been the other way around. If the function were increasing instead of decreasing, it doesn't make any difference. If I can define some value k that is between f of A and f of B, let's just say right there, right? Then isn't it guaranteed that somewhere on that interval, my function has to pass at least once through that horizontal line? There's no way around it, is there? If I can't pick my pen off the board and I have to start there and end there, and it's a function, so I can't violate the vertical line test, right? I can't do something sneaky like go out like that, because then I'd be violating the vertical line test, right? Does that make sense? So then there has to be at least one place where that's happening, and that place where it's happening we'll just call C, right? So then K is just equal to f of C. Now it could be happening multiple times if my function's doing this, right? If it's going like that. Is that us?
Yeah.
Oh yeah, we're a short period today, yeah. Okay, that's about all I want to do anyway. Okay, tomorrow we'll go to the lab and work on this stuff. I'll put a new assignment up for you today.